All right, welcome everybody to our first Grasp on Robotics talk of the semester. This is the Grasp on Robotics talk seminar series where we invite guests from around the world to come and share interesting new robotics work with us. My name is Cynthia Sung. I'm faculty host for today's talk. As a quick reminder, you all are here in person, but if you want to review the talk later, recorded versions are online on our YouTube channel and website. And you also have the opportunity at the end of the talk to ask your questions to the speaker. But with that, I would like to invite our amazing speaker for today, Professor Wojciech Matusik. Professor Matusik is a professor in MIT's Department of Electrical Engineering and Computer Science, and he leads the Computational Design and Fabrication Group at the CSAIL. His research interests are in computer graphics, computational design and fabrication, computer vision, robotics, and human-computer interaction. Before coming to MIT, he worked at Mitsubishi Electric Research Laboratories, Adobe Systems, and Disney Research in Zurich. And he's received many awards for his amazing work, including the DARPA Young Faculty Award, the Sloan Foundation Fellowship, as well as an award for excellence in teaching. And so really excited to have him here today. As a side comment, I also had the honor of working with Professor Matusik during my PhD, and he taught me a lot of what I now know about computational design. So I'm very excited to hear what he has been working on over the last few years and all the new developments in how how computers can help humans to do design work. So with that, please help me in welcoming Professor Wojciech Matusik.
All right, great to be here. So the title of the talk is a little bit provocative. Let's see how it goes. Okay. So I want to tell you that I really study design in general, and when you think about the design is really everywhere. So if you're an automotive engineer, the design for you would be design of this beautiful car. If you are a chemist or chemical engineer, then the design for you would be design of new reactions, new molecules. If you are a software engineer, right? If you then design, then design for you would be design of novel software, then design of novel software architectures, novel algorithms. If you are a chip architect at NVIDIA, AMD, then the design for you would be probably co-design of both hardware chips and software on these chips, right? So overall, I really think design is everywhere. I think this is something to keep in mind, that really you can think of any creative activity that we do as a design process. And I would like to understand it. I would like to sort of study it in a more formal manner. This is a robotics seminar, so of course, I will try to emphasize more robotics applications. Over the probably last 10 years, I have been working on design of machines as well. So this is probably one of the more complex machines, that I built. This was commercialized as Inkbeat. This is a 3D printer that has a vision system as a feedback loop. So essentially, you can, in this case, the system is scanning the layers every time, and it does it extremely, extremely well. It's also multi-material, so you can essentially control everything at the pretty much voxel level resolution. And that also means that you can, build, print robots, right? So this is work that we have done, on applications of this technology, appeared at Nature probably a year or two ago. And this showed that using these types of systems, you can pretty much 3D print complete robots in one shot. You just basically send the files with these rigid soft materials. You print essentially different types of actuators, pneumatic actuators. You are printing also the sensors. Pretty much in one shot, you send it to the printing system, and then you wash out the wax at the end. And then you can essentially plug it into external hardware, to external actuation system, right? To pressure control system, and you can essentially run this. So what's really interesting that case, the fabrication was just a print of a button, right? This was just sending stuff to the printer, and basically a robot came out, and you could pretty much almost directly use it. So we are pretty much approaching the technology where the fabrication becomes really, really simple and easy. And what basically is going to be the difficult is the design. So in this case, the design process for this robot took really, really long time. So some very talented PhD students were basically designing these robots for a few months in order to get this to work. So this was the difficult part. So my questions really here are, how can we potentially make the design process easier? This is kind of what I am really obsessed about. And not to really look at just a single domain, I want to be outside of my comfort zone. So in this case, I'm studying it across a few different areas and try to generalize it. So the idea here is that I study different design problems. I'll show you only some subset of those. So I study metamaterials. These can be, of course, very useful for robotics as well in design of robots. If you haven't used metamaterials, I highly recommend you to incorporate them into the design of robotic systems. We also look at chemistry. Chemistry definitely outside of my comfort zone, but nevertheless, we do chemistry as well. And we also, of course, build these systems for design systems and study cyber-physical systems, which is a fancy name of basically for robotics. At least robotics falls into this category as well. So, of course, you cannot really solve this problem, can computer beat humans at design I think by answering a single question. You really want to really decompose it into, I think, at least a few questions that you would like to understand. And I would like to pose them now. So the first questions really are, and they are very, very important questions that you really have to understand and really analyze very, very thoroughly. The first question is, how do you represent design and design spaces? So that's question number one. Question number two, how can we potentially learn the design spaces more automatically? Question number three is, how, if you have a design, how do you find optimal performance of a given design? And question number four, how do we really bridge the gap between what's digital and real? Because a lot of stuff that we are going to be, of course, doing is digital representations. But in the end, at least in the case of robotics, we are very much interested in actually doing this using real physical systems. And there's obviously this discrepancy between digital representations, physical representations. So you want to basically ensure that this gap is as small as possible. So let's start with the first one. How do you represent design and design spaces? So overall, I have looked at this for a very, very long time, and I really explored a lot of stuff, pretty much everything that's possible. And I'm really coming to a conclusion that one of the best representations for designs essentially are programs. Okay? So if you really want to build, if you really want to actually build very good representations for designs, you should really try to represent them as programs. Let me kind of try to maybe give you an example how this would work. And I'm going to do it on the case of metamaterials or engineered metamaterials. So I'll basically show you what the state of the field was a few years ago. So pretty much in metamaterials or in architected materials, these are used pretty much across material science. Robotics also uses it pretty heavily. A few different communities work focus their attention on a lot electromagnetics, acoustics, and so on. When you look at it, the field is extremely fragmented. You basically have things like straight trusses, curved beams, cellular structures, triply periodic minimal surfaces, solid bulks. Basically, every single field is trying to come up with their own little representations And typically, people design them in the traditional CAD systems, right? So, and there are each of those basically are going to be represented slightly differently. So different subfields here, right? And each of them has different tools, different representations. So what we wanted to build is a unified representation for all of these materials. Okay, so how do we do this? We basically designed a specialized programming language for this. Very, very tiny programming language. You can, in formal programming languages, this is called domain-specific language. And this is domain-specific language is only targeting essentially architected materials. Let me show you an example how it works. So if you want to design this structure that looks like this, essentially you start with a number of vertices here. You specify these vertices. Then you first operation is edge chain. Then the second operation is which connects all of these vertices together. Then you have a surface operator, mirror, 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 object, right? And then basically, and as you can see, this complex structure is just represented using very small number of operations. Another structure, again, vertices, edge chains, lines, mirrors, and so on. Very, very simple, right? And you can actually visually represent this, that's something that looks like this, okay? So in this case, you really are going to have this pretty much dual representation. In one case, you can represent this metamaterial as a voxel or voxel grid, or you can represent it as a surface, or you can also represent it as a program. And this program representation is going to be much more compact and much better to manipulate with, and also going to store all of the semantic information about the structure. So what did we do next? Okay, so now that you have a programming language, then you can go to the literature and you can sort of pretty much take everything that's in the literature and you can convert this to the programs. So essentially, and of course, as you go, you also test whether you design the programming language correctly. If there are some elements that are missing, of course, you have to start adding this to the programming language. But through a few iterations, pretty much we narrowed down both the programming language and in this case, we were pretty much able to represent 95% plus of everything that people have really done. Yes.
You said a question, this mapping can't be one-to-one, right? Like for a given state, there must be many programs that can generate.
Absolutely. Yes.
So like, how would you define, like, do you have some way to say, like, this is a minimal representation for programming?
So at least you would like to be, so anything that people have built, you at least want to be able to represent this using your language, right? So if you cannot do this, if you cannot represent a given structure, then basically you typically, if you think this is an important structure, you have to pretty much go back and, you have to adjust your programming language, right? And there's a little bit of a back and forth between this. This is typically an iterative process that sort of involves a little bit of back and forth, a few iterations. And typically you would take 100 papers and basically you would just see, can I represent every structure in this 100 representative papers in my programming language? And if you do the matching correctly, you do the right refinement, you are pretty much done. So it's an iterative process, but typically it requires surveying lots of literature and working with the domain experts as well. So we can pretty much represent established structures once you have a program. Yes. No, absolutely not. You can pretty much, it's not. So, but this, you can incorporate a lot of these constraints in the language. If you want to have only symmetric structures, you can absolutely do that. Once you have a programming language, this programming language can act as a generative model. So you can start generating pretty much programs at random, right? And basically you can sort of start building really, really large repositories of different types of structures. And so what's really interesting is that, if you do the search very, very well, you can even find very unusual structures. In this case, we have found hundreds of new triply periodic minimal surfaces, very important structures in engineering. So just by designing the language right, we basically could discover things that people haven't really been able to do. So this was, I think, quite interesting. So key thing that you could already can imagine is that if you design your representation right, if you design your representation for the design space correctly, then search is going to be easier, right? And you will be able to find stuff that people haven't found before. All right, so you have a programming language and you can generate these metamaterials. But now I have, on one hand, I have material science folks. On the other hand, I have a programming language, and I'm giving them a programming language, and I'm telling you, please use this programming language. And the reaction is going to be, no way, I'm not learning a new programming language. And this was pretty much the situation up to the last 2 years or so, where program synthesis was pretty much unsolvable problem. But pretty much overnight, it became a solvable problem, where basically you can start building AI-based copilots that essentially allow you to synthesize these programs pretty much automatically, and they can be done by non-experts. So people who are not in computer science, who do not know how to program, they can start building AI-based copilot. We can start basically providing them with the AI-based copilot so that they can start using this. Typically, this ecosystem has a few different components, right? You have, in this case, we have a meta DSL, which is the DSL for domain-specific language for metamaterials, meta database, which you have to have a big database of structures, and also meta bench, set of evaluation tasks. So meta DSL, you have already looked, basically, I already showed it to you. So in this case, each structure that looks like this already can be represented as a program. Looks very much like Python, right? But it's a very, very specialized structure that's built on the top of Python. You also need to have a database of structures. So in this case, we constructed, essentially scanned many different types of papers. We converted each of these papers, the representative papers, to the programs. And then, you can then start sampling them, modifying them, mutating them, hybridizing them. And in the end, you get, if you curate this process well, you get on the order of 150,000 different structures. Yes?
Is this process of kind of curating this database, is it automated in itself? Meaning everything from the reading of the scientific document to the synthesis of your DSL program that will produce that?
So I am surprised how good it becomes. So these days, you can essentially throw in a given paper, a DSL, at a large language model, high frontier large language model. You can provide specifications of your programming language, and you will get it. Very, very close, very close. So not fully automated, but very automated. So, and then you have a compiler, which basically can then check remaining problems. Remember, you have a compiler, so I can actually take that, and also I can run the compiler and regenerate the structure. Right, and then I can compare what's in the paper and basically what's there. So this process, I believe, can be, right now it's semi-automated, but it can be absolutely, completely automated, where you can pretty much download lots of papers, then basically do these conversions. So, but we curate this. We want this database to be really, really nice. So we curated it extremely well. And the last part is basically meta bench. Meta bench is essentially a set of tasks that you use for evaluation. And of course, we train large language models for those. So here, a reconstruction task. In this case, the input would be a picture, sketch, right? And then the system automatically generates code for you for a given structure. Another one is inverse, where you specify the specifications for the material, its properties, right? And the system automatically synthesizes the code for that. Right. So, and then the third task is property prediction. You basically give it a given structure or an image of the structure or code if you want to, and the system automatically will tell you what the properties of the structure are. Right. So, So this is how these systems work. You know, the GUI, of course, is not great, but I think can be better. You know, so you can essentially import a picture. The system automatically generates the code, and then recreates the three-dimensional structure automatically, corresponding program. The users, of course, can look at the program if they want to. The experts can look at the program. They don't have to. And of course, you can make those structures if you want to. Of course, you can also do editing tasks. So if you want, you can specify, or you can specify the properties of the structures, right? And the system automatically is going to bring the code that has the given property structures, the structures with the given property. You can also provide, if you want to, you can provide the sketches. Right, you can paint a given structure. In this case, the system automatically is going to do the vision language system. Vision language model is going to be automatically converted to the code. So in this case, I say write a metamaterial procedure that looks like this, right? And the system is going to recreate those. Yes.
And we can, find combinatorial as well. So what is the how much of that search space needs to be stable or no? Where to put that? To what extent is it the emerging area that's more or less slow, or is there a stable area? I was curious what is cut off. What is your intuition?
So I think I will get back to it near the end of the talk. But I think overall, I think this really points at the limits of the current machine learning systems. So think about it basically in terms of the coding. You probably, most of you guys are using coding copilots these days, right? So coding copilots, of course, have they have been trained on lots of code, and they can pretty much recreate a lot of the components. They can stitch together pieces of code, from many different. You think of this almost as the current coding copilots have seen a lot of code, right? And they can pretty much recombine this code in the novel ways to produce new programs. Can they create completely new algorithms? That's very debatable, okay? So their extrapolation powers, and I think there are definitely limits. If you want to create, for example, completely new classes algorithms, that will be, of course, much more difficult. So this is probably where they really hit the wall at the moment. But I think it's very, very similar to these. So what we are trying to do is pretty much build AI coding copilots and domain-specific languages, not for computer science. And I want to just mention that we have been building these domain-specific languages for many, many years. But as I said, for the last 10 years or so, this was really not very, very relevant. And now, essentially, building these domain-specific languages for non-CS, of course, becomes much more important because the users can actually start using this. A few examples. We have built things for chemistry. This is called a system called Polygrammar. So it's a specific language for expressing polymers. We have built these systems for robotics. So we had a DARPA program on designing cyber-physical systems. We build robots, drones. So in this case, it's hybrid UAV vehicles that were pretty much could be expressed using these domain-specific languages. And we have built one for walking robots as well. So this was a work probably from 5 years ago. And now this is kind of the more preview of what's coming. We are really converting all of these systems to DSLs. So this is a robot DSL plus Copilot. So we are building basically domain-specific languages, specifically targeting robotics. This is one of the application areas where pretty much any robot design can be expressed in this very small programming language. And of course, you want to couple this with AI-based copilots. In fact, to be really precise, we in this when you have to deal with robotics, it's not just one domain-specific language. You have to design a whole suite of programming languages. One of the programming languages is just for expressing structure and control. Another programming language is to express the whole world where the robot is interaction. Another small programming language is used to express the task. And another basically is doing just evaluation. So basically evaluation of the robotic systems. So I'm trying to build these tools for the community. If anyone wants to collaborate on these specific problems, we are of course very, very open to build this, because in the end, these are the tools that hopefully you guys would be using in the future. So if we could express everything that we do in robotics using these highly specialized programming languages, then you can actually share all of the data across community. So each of the essentially all of these environments, all of the robots, can be the research will be overall much more reproducible. So I think hopefully this line of research for robotics makes sense. And of course, you couple it with in addition to building large repositories, you can of course couple it with the copilots, which basically compile everything to the right simulations, to the right URDF files, and so on. So we basically work as essentially the glue that pretty much glues all of these components together. And you can of course specify, write in natural language. I want a robot that does this and this, and this automatically synthesizes the corresponding robot structures. And of course, you can build some small toy pieces right now. These are just toys for now. But of course, since we are using all of the components from the standard databases, all of the components can be purchased directly. So the systems can automatically build for you bill of materials, link to the right databases or components, and so on. So if you build these compilers really, really correctly, I think hopefully this is going to be a nice tool that robotics community can use. All right. So hopefully this sort of this resolved the question of how we build design and design spaces. Let's move on to the slightly more difficult tasks. The second task is really how do you really learn a design space? And I think this is a much more difficult problem because as I showed you, when we designed these domain-specific languages, this was pretty much highly curated. And I think it really makes sense to actually spend time on this because, in the end, if the whole community is going to use it, you're better design it right? But in some application areas, you don't really have time or energy really to design specific languages. So can you potentially learn these languages? Can we do it automatically? So you might think, well, this might seem easy, but I think, and it might building this generative model. There are already lots of techniques in machine learning that can essentially do this. But they pretty much start to fall apart when the experimental data sets, where your data sets are extremely small. So when your data sets are small, and let's take chemistry for an example, in a given category, you are not going to have a lot of experimental data. You are going to have 20 designs, okay? 20 molecules, 20 designs. How can you build something from 20 designs? This is extremely, extremely challenging. How can you build a design space from only 20 examples? Let's try to see how potentially this can be done. Let me show you one approach. This is for molecules, but express pretty much all of the robots as graphs as well. So pretty much the same concepts really are going to apply to robotics as well. So how would it work? You essentially start with the collections of the designs, represent each design as a graph. And then you are going to build this language automatically. How do you do this? We basically use bottom-up search to automatically generate these graph grammars. So how it essentially works is that you start with you start analyzing all of these design graphs at the same time, and essentially you are looking at sort of fusing different components together. But you are going to do this fusion pretty much across all of the designs at the same time. As you fuse the elements of the graph together, essentially this tells you you are building the language, right? So in this case, I am selecting some components of this grammar and some elements of the grammar, and I'm doing progressive collapses of the edges. As I'm doing these collapses, I'm inserting the rules of the language, right? How things basically should be synthesized. And essentially, you keep doing these collapses until you end up with the only one node for each, in this case, for each molecule. If you do it for robotics, it would be one node for each robot. In the process, essentially, you have constructed the whole programming language. Of course, there are many possible ways in which you could do this. There are many ways in which you can do these collapses. But we frame this as an optimization process. So pretty much you can learn these languages or graph grammars in this case as an optimization process. And you're really optimizing for two different metrics, diversity and validity, and they kind of are contradictory. On one hand, the diversity means that how expressive your grammar is, and the other one is how valid the designs that are spitting out are going to be. So basically, you are really trading off between these two different metrics. If you increase the diversity, probably some of the designs that are going to coming out are going to be less valid. So you can pretty much nicely trade off about this, but you can put it into the optimization objective, and then you are going to get the right grammar. As you can see, you can really have trade-off between validity and expressivity of your language. So this just shows you that for different metrics of diversity and validity, you are going to basically get different programming language. And we also show that this works extremely, extremely well. So if you have low data regimes, and I'm claiming that in most of the design problems, you are going to be in very low data regimes, basically this stuff pretty much can beat all the competition. I think that's not important. So the key insights from here is that the symbolic representations are very, very powerful. If you were to use, for example, deep learning approaches and try to learn a generative model based on 20 examples, wouldn't actually work. What's also very important are automatic checkers and oracles. So, for example, checkers that tell you when that you have within this loop that sort of check for validity of the design are extremely important, and they can really prune out a lot of parts of the invalid space. And also, what you can do, you can also nicely incorporate expert annotations. So experts can actually be very, very helpful in designing these languages. For example, they can add annotations and tell people this part fits together, or this group of components fits together nicely. So you can very nicely incorporate lots of annotations from the experts. So even in this low data regimes, this can work nicely. Let's move on to the next question. The next question is, how do you find designs with optimal performance? And let me show you a few different examples here. So typically, right, we have defined the design space, right? This was done in the previous sections. But in most of the cases, we don't necessarily just care about the design. We also care about how the robot in this case performs. For example, how fast does it go? Or how much does it cost, and so on. So performance metrics are evaluated for each of the designs. Typically, you have a function that goes from each design to performance values. What's also much more difficult is the so-called inverse process, right? So you start with a given setting for the design metrics, and you want to find the point in the design space that has the best possible setting for these metrics. Again, how can you basically do this if your exemplar domains are extremely, extremely small? And as I said, in most of the experimental areas, these data sets are typically not very large. You can really count maybe 20 to 30, maybe 50 different examples. That's it. So a typical computational design workflow in this case would work as follows. You essentially start with, you are building a generative model. Generative model builds lots of designs. And then you also couple it with the predictive model. Predictive model essentially is it's like a scoring function, essentially that scores each of these designs. And if you couple them together, right, you are going to eventually get the designs with the best performance characteristics. What's also very important is that you can start building both of them at the same time. So you can basically both build a generative model and the predictive model. You can basically start you can create them all at the same time. So both the generation and the prediction basically can be done completely in a single step. So what I also we have built here is that in most of the building of the predictive models, I think the intuition here is that if you really want to build a very predictive model, you have to figure out what is close to what, right? So because in the end, you are doing some amount of interpolation. So if you want to know what the properties of a given robot is, you want to know what are the similar robots in that space, right? So in our approaches, we essentially, whenever you have a space of programs, basically you are going to the comparison of how close a given robot is to a new robot based on how similar these programs are. And that essentially allows you to build these predictive models while you are also optimizing for these grammars. So this is essentially this approach where you build both the generative model and the predictive model in a single shot as a single optimization process, it will allow you to work with very, very small data sets and also make sure that the designs that you are creating are going to be preserving some of the metrics that preserve the manifold that you are building at the same time. This can be structured as a joint optimization problem. So as I said, both the generative model and the predictive model can be built at the same time. What is really nice is that in this very simple settings, right, you can start creating very novel types of designs. And in this case, you can do this for multi-objective value, for different types of multi-objective characteristics, right? And then, for example, you can get these Pareto fronts of the optimal designs that have optimal metrics. In this case, we looked at molecules, design of molecules that have optimal trade-off between permeability of the molecule and selectivity. So these are two of the very important properties. And extract pretty much the Pareto front, the designs with the best optimal values. Again, the input data set was extremely, extremely small. It had, tens of molecules. And what's really interesting that this Pareto front exhibits basically you are designing molecules that have very nice properties that pretty much combine elements, optimal design elements from different parts of this small data set. And in fact, we even synthesized, we build these molecules, and indeed, basically, these properties really look really, really nice. So that's case number one. That was case number one, building completely data-driven processes. We also look at the process where where the simulation is possible. And the specific area that we have been looking at very, very closely is the so-called differentiable simulation. So in differentiable simulation, we are building simulators that allow you that also give you derivative of the simulation with respect to different design variables. So typically in any type of physical system, whenever you do dynamic simulation, you can build a computational graph. In this case, when you sort of we are tracking the velocity and position of this little mass spring system. I can write the ODEs for this. And as you can see, I can compute what each of the values for position and velocity are at each time step, right? At the end, I can form the so-called loss function. This is the difference between what I want and what the simulation produces at the end. In differentiable simulation, I can essentially compute the difference between what I want, right? And what the system currently gives me. And this basically forms the loss. And I can then propagate the values of this loss through the whole system. And I can tune and I can compute specifically sensitivities of derivatives with respect to different design variables. And in fact, this is very, very powerful because now you have you have access to continuous optimization toolbox that you can start optimizing designs. This is extremely useful for many different applications. One of them is system identification, where you basically can look at measurements and you can sort of optimize the whole system parameters. And you can, of course, do it for initial condition optimization. And of course, you can also use it for optimization of the design parameters. This is part of the project that we have been doing a few years ago. This optimization of the hybrid UAV systems. In this case, we have been optimizing both control and the shape of the system at the same time. So in this case, the controller was expressed using a neural network controller. And we basically wanted to have a UAV that can take off vertically. One controller should transition to wing-based flight, and then the same controller should also allow it to land. So at the same time, we are also optimizing the shape of the continuous variables of this vehicle. And in fact, pretty much, this is possible. You can do it. In fact, we have also built these vehicles. We have built both the vehicles for aerial vehicles that look like this and perform. And we also built the underwater vehicles that basically, the underwater gliders that can essentially glide underwater. We have also applied this technology to optimization of soft fish. In this case, the simulation is more difficult. We have to use dynamic finite element analysis to do the simulations. And in this case, we show that you can pretty much optimize if you optimize only for control or optimize only for shape. You are not going to do very well. But if you start optimizing both for the shape and the control at the same time, pretty much you get very different shapes. In this case, we actually show that if you want to optimize this soft fish for different objectives, right, you are going to get very different types of fish. So, for example, if you want a fish that swims very, very, very fast, but it's not very energy efficient, you will get this fish, medium speed, this fish, and so on. So depending on your objectives and trade-offs of the objectives, you are going to get different control and different shapes depending of what your objectives are. But as you can see, you are going to get a very nice Pareto front of different designs and different controllers that are associated with each design. And we have, yes.
In that case, for example, are you also optimizing the controller?
Yes, controller. Both control.
Some very specific form of controller.
Yeah, so this pretty much you can plug in anything that's differentiable. We use small neural network controllers for doing this, but you can really pick whatever you really want. We have done the same thing for fluidic systems. So this is topology optimization of fluidic twisters, where you can do topology optimization of the whole system with millions of different variables. And more recently, we have coupled this with we have built differentiable Navier-Stokes fluid simulations, where you can optimize both the shape and control of this pneumatically actuated hearts, right? So in this case, you have both the differentiable fluid simulation that operates on very, very high resolution grid. And you also have that's coupled to geometric controller, all differentiable, and you can pretty much compute both the shape and control at the same time, even for the soft structures. So just an example of a neurally optimized heart, where you have again, you started with some design, and you can show that this highly optimized designs. And of course, now you can print it as well if you really want to, using the printers that I've shown before. The last part that I would like to tell you about is something that's actually very important. Is really how do you really bridge the gap between digital and real? And as you have noticed, we have been doing a lot of stuff digitally so far. But the dirty little secret is that you can do all of this stuff in this computational design in a digital environment, but in the end, if it doesn't really match the reality, there's really no point, right? This has no point. So you have to ensure that there's really good match between these two, right? So when you look at this, right, you can visualize this gap between simulation and reality as follows, right? So imagine you have a design. I can take this design and I can use simulation, and I'm going to get certain parts of some properties for a given design. And then I can also fabricate this design and measure its properties, and I'm going to get these property values that look like this. And that the difference between basically what's simulated and what's measured is the so-called, people very often call it sim to real gap. How do we solve this? Okay, so we solve this pretty much by building new classes of simulation systems. So we look at the simulators and we replace selectively different parts of the simulation systems with more general, in this case, more general expressions, in this case, neural networks. And we have applied it, to a different examples. We have done it more recently. We are doing a lot of robotics applications. So how does it really look like? So we basically have a classical. So if you have a classical physics simulator, basically it's a dynamic system, right? So you go from state 0, you apply simulations and so on, and for many different steps. In each simulation block, you are solving typically a PDEs. And we are going to essentially replace these, we are going to replace, in this case, material properties. In this particular project, we are replacing material properties with tiny little networks. And when you think about it, people really don't know how to really model materials. So it makes perfect sense to replace these components with a neural net. So if you couple this with a differentiable system, then you can actually start optimizing the parameters of these networks directly from small number of observations. So the idea here is that you have, for example, video data, right? And then you have a simulated system. You can form the loss even in the image space between what's simulated and what's real. This becomes a loss function. And then you can backpropagate this through the sequence of simulations, and you can start optimizing the parameters of these neural nets. And pretty much this can be applied extremely nicely to robotics for modeling different types of actuation systems, contacts, and so on. So different parts of the robotic simulation systems can be selectively replaced. And so some parts potentially can stay as a classical methods. For example, time integration can stay as classical method, but certain components that typically are not modeled very well can be selectively replaced using neural networks. This hybrid neural PDA approach works extremely well because it's very data efficient, right? So you still have so first of all, you can really tune these small tiny neural networks that are injected into the system using a small number of very small number of experiments. So data efficiency is extremely high. Only small number of observations, you can pretty much tune the material properties of the system. And if you compare it to standard machine learning approaches, this really works extremely well. So when you have, for example, training data looks like this and ground truth. So if your training data looks like this and you would like to generalize it to different structure, right? The ground truth looks like this. This is how this system would perform. And if you use, for example, pure machine learning approach without any physics, using, for example, graph neural networks, of course, it doesn't generalize extremely well. So what I'm trying to tell you that if you start building simulators that are both hybrid and that are both classical and neural, you can get very good fit between simulation and reality. And also they are going to generalize very, very well to new types of applications. All right. So these were the 4 questions that we really, that I thought are very, very important in answering this question: can computers beat human at design? And I think we are really getting close. So I want to just tell you that a few lessons that I have learned over there. So the key thing is representations. I think if you design the representations for your design and design space, I think computers are incredibly good through searching this space and finding for you really amazing designs. And you know, if you define what that search space is, and especially if you involve, you know, humans in the process, they will do an amazing job, and they will find stuff for you that you really haven't found before. So essentially, this has, you know, we have shown that this really works very, very well. On the process of design, I think what we can do today, pretty much almost automatically, is design of new things with optimal trade-offs of performance trade-offs. And I think at the high level, it basically works as what follows. These methods works as follows. Imagine that you have some designs and the input designs that are very, very good with, you know, that at, you know, property A, and some designs that are very, very good at property B. But there are no designs that have very good, you know, performance both for property A and for property B. These new computational methods essentially break up these designs and figure out which components of the first design is responsible how good property A is, and the other one basically is breaking up the design process to tell you how good the property B is, and basically recombine them together into something that has both good property A and property B. So this works, in my opinion, very, very well in terms of multi-objective optimizations, right? And I want to sort of say that many engineering problems are about optimizing for multiple properties. So this is incredibly useful, right? So being able to optimize and for multiple properties at the same time, I think, and have algorithms that do this automatically, I think is very, very useful. And computers are exceptional at this, while people are not very good. So basically, people are typically very good at optimizing for a single objective, but you tell them optimize basically for combinations of different objectives. I think that people typically, or experts, are not very, very good at that. I want to sort of move on to what the limitations are. The limitations in computational design really are about extrapolation. And I think this is also the problem with a lot of the machine learning techniques. So imagine that that I have essentially that I am designing propeller-based engines. Okay, I have a collection of propeller-based engines. Right, I can probably start synthesizing many different variants of propeller-based engines, but no current method is going to actually create a jet engine for me. Okay, so these are basically, this is not something that current systems really can do yet. Basically, make tremendous leaps in designs. They are very, very good at sort of doing this multi-objective stuff, or searching the space for different possibilities, but making big leaps in design, I think, are extremely hard, and this is not something that the current systems can do. So the question is, how do we extrapolate? And really, if you want to think about how do we extrapolate, I think the best way to extrapolate is really to study scientific breakthroughs. So, and I have spent a lot of time, actually, the last few years studying scientific breakthroughs, sort of thinking, how do these really occur? And I think it's really important to start looking at this. And I think this is not something that current machine learning systems, in my opinion, do. I think the right approach looks like this. The right approach, in my opinion, is not to amplify the amount of data, but to reduce. So essentially, if you really want to extrapolate, if you want to really innovate, you have to understand the rules of the game. So you have to really, in any single game, in any single domain, you really have to go in and sort of understand what are the rules of the game that I'm playing. And typically, the number of these rules is extremely, extremely small in each domain. So basically, you have to go through this funnel and basically figure out what are the main assumptions that really my game has. Okay? So think about it at a very, very high level. You know, really, whenever you're building a robot, right, you are really playing a game. Okay, you are playing a game. How can I build a better robot? Okay. And you know, you are building a robot, right? And you know, imagine basically your game has a scoring function, and I'm going to get maybe to 100, and no matter how well I play, I'm hitting 100. Okay. Let's imagine that I want to hit 1,000. Imagine basically I want to build a new robot that's going to give me a 1,000 score. How do I do that? The only way to do this is really to change the rules of the game. Right? This is key thing that you have to really remember. If I want to really make these leaps in how we approach the problem, first of all, I have to understand what the rules of the game are that I'm playing, because every one of you is playing a game, whether you know it or not. So it's very important to understand what the rules of these games are, and then you have to sort of think about how can I, which of these rules can I break to get to the better score. So with this, really, I would like to really end, and I really think that the lessons learned from this is that at a very, very high level, I think computers can beat humans at design, and they're starting to beat humans at design. But I think the best way is really to make these centaurs, human-computer hybrids, that really utilize really utilize the best of both. Right? Computers really can search the vast spaces, design spaces, but I think humans really should really think very, very hard what the rules, what these design spaces are. How do I really represent this design space? What is that search space? And how potentially can I start breaking the rules of my design spaces? So with this, I would like to end, and I'm open for questions.
Thank you very much. We have time for questions.
Thank you very much. Very interesting talk. I was wondering if you could tell us a bit more about the sim-to-real part. You said that the loss is in image space, but I was wondering how to make sure that the optimizer doesn't have spurious features like the illumination or whatever.
So first of all, your loss can be whatever you want. Okay, so but as long as it has to be some difference between your observations and what the simulation output is. In this case, I think doing the image space is just very practical because you can take it with you can do it with your cameras. But of course, if you have access to the observation data on your robot, for example, sensor data that comes from the robot, you can absolutely do it directly in the sense, your measurement space. So image is just convenient, but you can do it however you want. How do you do it? So when you build the image space loss, it's basically invariant to different parts. So typically you want to build special types of loss functions that are invariant to these illuminations. In fact, in this work that I was showing, we built the loss function such that basically the loss is invariant to illumination changes. Yeah. Yes.
How do we think about moving rules that are happening?
So typically, I want to just say that whenever you approach a given design problem, I think typically there are certain types of assumptions that you are making. These assumptions are the rules of the game you are playing. Okay, and it's very important, and very often, your assumptions are in your head, but they are never formalized. what I'm arguing for, that you should absolutely formalize what these assumptions are. So whenever you do a project, write down the assumptions that you are making. These are the rules of the game that you are playing. And then think about, basically, your assumptions are going to constrain what you can do, okay? Essentially, think of an assumption as a constraint that binds you, right? And I'm trying to say is that typically big breakthroughs come from relaxing this constraint. This is how basically, so let's give, there are many examples, but for example, let's take, for example, Uber. How Lyft or Uber changed, the industry, because they changed the assumptions, they changed the rules of the game, right? Yes.
This axiomatic design also relate to basically the completeness and the consistency of the design space.
Absolutely, absolutely. You have to make sure that all of the assumptions are consistent. Basically, you have to make sure that there are some solutions.
Also
Complete, yeah, of course, of course. I think ideally you want to spell out as much of the stuff that because lots of stuff is, in your head, right? It's there. It's just never put on paper or in the computer. That's the problem. You have them, they are just not explicitly stated. And I'm just trying to say that we should absolutely state this, because this will help you in your research. Yes.
A lot of the time, I believe the new knowledge comes from like different discipline interactions. And of the design approach that you mentioned, is there a generality in different discipline, and can we learn from other disciplines through these computational designs?
At least this is what this is working for me. In order, in my opinion, to make something more general, I think it's good to look at a few different fields. So I really think these fields help each other. Of course, there's lots of domain-specific knowledge, but there's also lots of things that are nicely transferable between the fields. And I think it's very, very useful to actually look at this across a few different fields, so you come up with something that's not just overfit to a given domain. So I think this is useful, and I think it's not that, I think it gives you different perspectives, because you see connections between different things at the same time. Yes.
But when you were talking about learning the design spaces, and one of the steps was a search over the graph structures to see the graph generating rules.
Yes.
What kinds of assumptions do you have to sort of already start with in terms of maybe like needing something that looks sort of like a graph structure in your data representation in the first place?
So typically, a lot of the designs can be represented using graphs. Essentially, think of a design as collection of entities. And so these are the nodes of the graphs, and edges are the relationships between these entities, right? So I think it's very, very natural to really think about designs as graphs, at least. And typically you can make them hierarchical and so on. So these methods essentially build the grammars or small, tiny programming languages that basically can express different types of graphs. But there are many possible of these domain-specific languages that express these graphs, and you have to basically find what's the best one. Okay, and in my opinion, it's really nice to build basically. It's really good to do it to do this optimization. It's good to find these. It's important to find these the language that essentially where. It's important to find languages that also is able to predict the properties as well. Because you can think about basically each of the underlying structures also going to have associated properties, right? So whatever your language is going to generate also is going to actually have now is going to have associated properties, right? So you want to make a language such that this language essentially can express stuff, but also at the same time predict properties of anything that's synthesizing at the same time. That's a high level idea. Yes.
Amazing talk. So really, really inspirational. I had a question regarding. I suspect that one of the things that's sort of important in design is actually sort of surfacing what the criteria are for design. So think about a field like architecture, even like designing a robot. A lot of these things that are important, robustness, rigidity, ability to deal with sand or grit, all that stuff, are actually sort of hard to, or can be hard to for a human to predict.
Yeah.
I'm wondering if you have any thoughts on ways to sort of either surface or sort of capture what design optimality means.
That's hard because I think, I think many people have hard time articulating this. I think it's not that it doesn't exist. It's more about articulation. That's really and I'm trying to say that we have to learn how to articulate this better, because we will just, if we can articulate it ahead of time faster, this will basically, we will understand. I really think this comparison to playing the game is very, very adequate, because very often you are essentially trying to play that game. You kind of intuitively understand what's going on, right? But and sometimes you don't really know what the score is, right? Sometimes right, if your paper gets accepted, maybe it's a high score, right? If it gets rejected, maybe no, right? But playing that game, like understanding what these rules are, I think and trying to articulate it as as much as possible. I'm not saying that you can do everything, but I think as much as you can do, I think it's going to really be extremely helpful. And especially, I think early on, so you actually know what you really want to be breaking. Because we are really, like when you think about, all of the research, amazing research that you guys are here, you are really breaking the rules of the game, right? This is what every single person here is doing, right? You are trying to come up with something that hasn't been done before. How do you do this, right? You can actually do this maybe incremental little changes through, or you can basically make these bigger changes, right? But I think, but I think these bigger changes really come from questioning the assumptions that you have made.
Please join me in thanking. Let's think again. All right, and you can join us next week for our next Grasp on Robotics seminar series. See you all then.